Hello viewers, in today's session we are going to discuss the relationship between hyperbolic functions and circular functions. Circular functions are also known as trigonometric functions. So in this class we are going to derive the relations between hyperbolic functions and circular functions, right? So let us see how we can derive the formulas which connects the hyperbolic functions and circular functions. So let us start. So now let us first quickly define the hyperbolic functions. Now the hyperbolic sine of theta is defined as e raised to theta minus e raised to minus theta over 2, right? So this is the notation for hyperbolic sine of theta. So here we write sine and then we have h, and here we have theta, right? So hyperbolic sine of theta is defined as e raised to theta minus e raised to minus theta over 2, where theta is either a real number or a complex number. And similarly we can define the hyperbolic cosine of theta as e raised to theta plus e raised to minus theta over 2, and the hyperbolic tangent of theta is defined as the ratio of hyperbolic sine of theta and the hyperbolic cosine of theta. So here we write the value of hyperbolic sine of theta, that is e raised to theta minus e raised to minus theta, and here we have hyperbolic cosine of theta, that is e raised to theta plus e raised to minus theta, and these twos, that is this two and this two, get cancelled, right? And similarly we can define the hyperbolic cotangent of theta as 1 over hyperbolic tangent of theta. So this is simply e raised to theta plus e raised to minus theta divided by e raised to theta minus e raised to minus theta. So taking the reciprocal of e raised to theta minus e raised to minus theta divided by e raised to theta plus e raised to minus theta. And we can also define the hyperbolic cotangent of theta as the ratio of hyperbolic cosine of theta and hyperbolic sine of theta. Now, similarly, we can define the hyperbolic secant of theta as 1 over hyperbolic cosine of theta. So here we can take the reciprocal of e raised to theta plus e raised to minus theta over 2. So this is 2 divided by e raised to theta plus e raised to minus theta. And similarly, we have the hyperbolic function, that is cosecant of theta, that is 1 over hyperbolic sine of theta. So taking the reciprocal of e raised to theta minus e raised to minus theta over 2, we have here 2 divided by e raised to theta minus e raised to minus theta. So this is how we can define the hyperbolic functions. So now here it is important to observe that the hyperbolic functions are defined in terms of the exponential function, right? So now let us come to the circular functions. Circular functions are also known as trigonometric functions, and we have 6 trigonometric functions, that is sine theta, then we have cosine theta and tangent theta, then we have cotangent theta and secant theta and cosecant theta. So these are the 6 circular functions, and here we have the six hyperbolic functions. And now we are going to derive the relationship between the hyperbolic functions and circular functions. So let us see how we can connect sine theta with the hyperbolic sine of theta, then cosine theta with hyperbolic cosine of theta, then tangent of theta with hyperbolic tangent of theta, and cot theta with hyperbolic cotangent theta, and secant theta with the hyperbolic secant theta, and cosecant theta with hyperbolic cosecant theta. So now let us start with the famous Euler's formula. Now the famous Euler's formula states that we have e raised to I theta, where this I is the iota, that is equal to the square root of -1, or I square is equal to -1, and theta is real or complex. And we can now write e raised to I theta as cosine theta plus iota sine theta, right? So now if we replace this theta by minus theta, then this formula becomes e raised to minus theta is equal to cos theta, and here we have minus I sine theta. So we have these two important results to start with, right? So e raised to I theta is cosine theta plus iota sine theta, and e raised to minus I theta is equal to cosine theta minus I sine theta. Now if we add these two equations, then we get e raised to I theta plus e raised to minus I theta, and here these two quantities get cancelled, right? And we have 2 times cosine theta. So cosine theta is equal to e raised to I theta plus e raised to minus I theta over 2. So this is an important result to start with. And similarly, if we subtract equations 1 and 2, here we have added equation 1 and 2, and if we subtract equation 2 from 1, then we get e raised to I theta minus e raised to minus I theta is equal to 2I sine theta, because in this case these two terms get cancelled, and this negative becomes positive, and we have I sine theta plus I sine theta is 2I sine theta. So now we have another important result, that is sine theta is equal to e raised to I. So we have e raised to I theta minus e raised to minus I theta over 2 times I, right? So this is the second important expression, right? So we have now these two expressions, and these two expressions are sufficient to derive relationship between hyperbolic functions and circular functions, right? So let us derive the relationship between hyperbolic and circular functions with the help of these two important expressions. So now let us replace this theta with I theta, right? So replacing this theta with the product of iota and theta, so that now this expression can be transformed as cosine I theta. Replacing theta by I theta, we have e raised to I times I theta, then we have e raised to minus I times I theta over 2. So now simplifying it, we have e raised to I times I is I square theta, and here we have e raised to minus I square theta over 2. Now I square is equal to -1, so we have e raised to minus theta, plus e raised to theta, because minus I square is equal to 1, right? And here we have 2, so this can be written as e raised to theta plus e raised to minus theta over 2. And we can easily see that e raised to theta plus e raised to minus theta over 2 is equal to the hyperbolic cosine of theta. So now cosine I theta is equal to cosine, that is the hyperbolic cosine of theta. So this is the relationship between the cosine of I theta with the hyperbolic cosine of theta. So now let us replace theta by I theta in this expression. So we have sine of I theta, that is equal to e raised to I theta. So we have I times I theta minus e raised to minus I times I theta over 2I. So we have e raised to I square theta, then we have here minus I square theta over 2I. Now I square is equal to minus 1. So here we have e raised to minus theta, and minus I square is 1. So we have here simply theta. And here we have 2I. So we can also write this expression as 1 over I times e raised to uh, theta minus e raised to minus theta over 2, taking negative 1 common. So here we can write the negative sign, and we can reverse these two terms. So we have here e raised to theta minus e raised to minus theta over 2 multiplied with this factor minus 1 over iota, right? And here from the definition of hyperbolic sine of theta, we have e raised to theta minus e raised to minus theta over 2. So this expression can now be replaced by hyperbolic sine of theta, right? Now minus 1 can be replaced by I square. So here we have I square for minus 1. Here we have I, and this is hyperbolic sine of theta. So here I and I get cancelled. So we have I and hyperbolic sine of theta. So now we have this relation, that is sine I theta is equal to I times the hyperbolic sine of theta. So here we'll write this relation, sine of I theta is equal to I times sine hyperbolic sine of theta. So this is the second relation between hyperbolic sine and the trigonometric sine. So now let us divide sine theta by cosine theta to get the expression for tangent of theta. So tangent of theta is equal to sine theta over cosine theta. Sine theta is e raised to I theta minus e raised to minus I theta divided by 2I. And here we have cosine theta e raised to I theta plus e raised to minus I theta divided by 2. So now this 2 and this 2 get cancelled. So we are now left with 1 over iota. Then we have e raised to I theta minus e raised to minus I theta divided by e raised to I theta plus e raised to minus I theta. So the expression for tangent theta is given by this expression. So now let us replace this theta by iota times theta. So replacing theta by I theta, we have now a tangent of I theta and here we have 1 over iota, and e raised to here theta is I theta now, so this is I square theta. Then we have e raised to minus I square theta divided by e raised to I square theta plus e raised to minus I square theta, right? And I square is minus 1 and minus I square is plus 1. So we have 1 over iota, and e raised to here we have minus theta, then minus e raised to plus theta divided by e raised to minus theta plus e raised to theta, right? So now taking negative 1 common in the numerator, we have now minus 1 over iota and e raised to theta minus e raised to minus theta over e raised to theta plus e raised to minus theta. So now this expression is equal to the hyperbolic tangent of theta. So here we have e raised to theta minus e raised to minus theta divided by e raised to theta plus e raised to minus theta. So now tangent of iota theta is equal to minus 1 over iota, and this expression is equal to the hyperbolic tangent of theta. So here we have hyperbolic tangent of theta. Now minus 1 can be replaced by I square. So we have now here I square over I and hyperbolic tangent of theta. So I and I get cancelled. So we have now a tangent of iota theta is equal to I times the hyperbolic tangent of theta, right? So this is the third relation. So here we can now write tangent of iota theta is equal to I times the hyperbolic tangent of theta. So now there is another way to derive this relation, right? See, we can directly write a tangent of iota theta as a sine of iota theta divided by cosine of iota theta. So now taking the help of these two relations, we can now write sine I theta as I times hyperbolic sine of theta, and cosine I theta is equal to the hyperbolic cosine of theta. So now this expression is equal to hyperbolic tangent of theta due to this definition, that is hyperbolic tangent of theta is equal to hyperbolic sine of theta divided by hyperbolic cosine of theta. So we get the same relation here by using this definition of tangent of iota theta, which is equal to sine I theta divided by cosine I theta. So now let us derive the other relations. So here we have cotangent of iota theta can be written as 1 over tangent of iota theta. So now taking tangent of I theta as I times hyperbolic tangent of theta, we have 1 over I, and here we have a hyperbolic tangent of theta. So now 1 over hyperbolic tangent of theta is equal to hyperbolic cotangent of theta. So we have 1 over iota, and here we have hyperbolic cotangent of theta. So now multiplying this I with this term, so multiplying cotangent I theta with I, we have now I times cotangent of I theta is equal to the hyperbolic cotangent of theta. So this is another relation. So here we can now write I times cot I theta is equal to hyperbolic cotangent of theta. So now let us write a secant of iota theta as 1 over cosine of iota theta. Now cosine of iota theta is equal to hyperbolic cosine of theta. So we have 1 over hyperbolic cosine of theta, and 1 over hyperbolic cosine of theta is equal to hyperbolic secant of theta. So here we have hyperbolic secant of theta. So now we have another relation here. So secant I theta is equal to the hyperbolic secant of theta. So now similarly we can now write cosecant of iota theta as 1 over sine of iota theta. Now sine of iota theta is equal to I times hyperbolic sine of theta. So we have 1 over iota, and here we have hyperbolic sine of theta. Now 1 over hyperbolic sine of theta is equal to the hyperbolic cosecant of theta. So we have now 1 over iota, and here we have hyperbolic cosecant of theta. So now multiplying cosec I theta by I, we have I times cosecant iota theta is equal to the hyperbolic cosecant of theta. So this is another relation. So here we can now write I times cosec iota theta is equal to hyperbolic cosecant of theta. So these are the six important relations between hyperbolic functions and circular functions. So viewers, this is how we can find out the relationship between hyperbolic functions and circular functions. And these are the six expressions connecting hyperbolic functions and circular functions. Now we can also express these relations in some other way also by replacing theta by iota theta, right? So if we replace theta by iota theta in these six relations, then we can modify these six expressions, right? So let us modify these relations by replacing theta by iota theta. So now let us take this expression, and replacing theta by iota theta, we have cos of I times I theta, and here we have cosine, that is hyperbolic cosine of iota theta. So here we have I square theta, that is I square theta, and I square theta is minus 1 times theta, that is minus theta. So here we have cosine of minus theta is equal to hyperbolic cosine of iota theta. Now from trigonometry, we know that cos of minus theta is equal to cosine theta. So this is simply cosine theta. So we have this relation, that is cosine theta is equal to hyperbolic cosine of iota theta. So now let us replace theta by iota theta in the second relation. So we have now a sine I times I theta is equal to I times hyperbolic sine of iota theta. So replacing this theta by I theta. So this is I square theta. I square theta is minus theta. So here we have a sine of minus theta. This is I, hyperbolic sine of iota theta, and sine of minus theta is equal to minus sine theta from trigonometry. And taking this negative sign over here, we have the expression sine theta is equal to minus iota sine hyperbolic sine of I theta. So we have this relation, that is sine theta is equal to minus I, and hyperbolic sine of iota theta. Now let us replace theta by iota theta in the third relation. We have a tangent of I times I theta, and here we have I and hyperbolic tangent of I theta. So here this is I square theta, that is minus theta. So we have tangent of minus theta is equal to I times hyperbolic tangent of iota theta, and tangent of minus theta is equal to minus tan theta from trigonometry. So now taking this negative sign to this side, we have tangent of theta is equal to minus I, and hyperbolic tangent of iota theta. So now we have the third relation. So here we can now write a tangent of theta is equal to minus iota and hyperbolic tangent of I theta. So now let us replace theta by iota theta in the fourth relation. We have I, then we have cotangent of I times I theta, and here we have hyperbolic cotangent of iota theta. So here we have I, then we have cot. This is I square theta, that is minus theta. So here we have minus theta and hyperbolic cotangent of iota theta. So from trigonometry, we know that cot of minus theta is equal to minus cot theta. So we can take this negative sign outside here. So we have minus I cot theta, and this is hyperbolic cotangent of iota theta, right? So this is our fourth relation. So we can now write this expression as cot theta is equal to 1 over minus I, here hyperbolic cotangent of iota theta. Now taking this negative sign to the numerator, here we write the negative 1, then we replace this minus 1 by I square, and here we have simply I square, right? So we have now written this negative 1 as I square, right? So I and I get cancelled, so we are left with I and hyperbolic cotangent of iota theta. So our fourth relation is now cot theta is equal to I times hyperbolic cotangent of iota theta. So now let us replace theta by iota theta in the fifth relation. We have now secant I times I theta. Then here we have hyperbolic secant of iota theta. So here I square theta is minus theta. So we have secant of minus theta is equal to hyperbolic secant of iota theta. Now from trigonometry, we know that secant of minus theta is simply equal to secant of theta. So we have secant of theta is equal to hyperbolic secant of iota theta. So our fifth relation is secant theta is equal to hyperbolic secant of iota theta. So now let us replace theta by iota theta in the sixth relation. We have I, then we have cosecant, and here we have I times I theta, and that is equal to hyperbolic cosecant of iota theta. So again, I square theta is minus theta, so we have I cosecant of minus theta, and here hyperbolic cosecant of iota theta. Now from trigonometry we know that cosec minus theta is equal to negative of cosecant theta. So here we have minus I and cosec theta, and this is hyperbolic cosecant of iota theta. Now here we can also express this result as minus 1 over iota. That is, here we have I in the denominator, and minus 1 can be taken in the numerator, and we have the hyperbolic cosecant of iota theta. So now this minus 1 can be replaced by I square. So here we can now write I square, and this I get cancelled. So we have now cosec theta is equal to iota, and here we have cosecant, that is the hyperbolic cosecant of iota theta. So our sixth relation is cosec theta is equal to I times the hyperbolic cosecant of iota theta, right? So viewers, these six relations can also be expressed like this by replacing theta by iota theta. So this is how we can derive the relationship between hyperbolic functions and circular functions.